Good morning, good afternoon, ladies and gentlemen. This is the session where we are looking into a very specific topic, which is maximizing and optimizing performance of renewable energy through using either any software type, smart technology and energy storage systems, so that you can actually have more control of what your actual assets are doing and when. And with us today, we have two super speakers from Wärtsilä that are going to tell us about a solution for this. And I'm going to unmute you, Jan. Let me see. No, I can unmute you. You're going to have to unmute yourself. Could you please introduce yourself?
Thank you. Yes, Jan Andersson. I'm a market development manager for Wärtsilä, based in Helsinki, Finland. I'm looking after our market development activities in Europe, especially in Germany and UK. So a lot of taking an insight into what is happening in the future, trying to promote and make our customers' business better and make more money for our customers.
Thank you very much, Jan. And you are today, where are you joining us from today?
I'm actually joining from my summer cottage. So I'm out in the archipelago at my seaside office. I'm very privileged to be so.
In Finland, right?
In Finland still.
In
yes.
Finland. See, so I'm in Madrid. So you see that this is a very international group here, just like the people in the audience. And Luke, please, could you unmute yourself and introduce yourself?
Yeah, hi. I'm Luke Whitmer, General Manager of Data Science in Wärtsilä in the Energy Storage and Optimization Business Unit. It's really great to see everybody saying hi from all around the world in the chat system. UK, Spain, Argentina, Mexico, Albania, UAE, all over. So yeah, really great to see everybody coming in. Looking forward to sharing what we can today. I'm in the US, near Washington, DC. I know everybody has probably seen some crazy things in the news. I'm safe. I live outside the city in the suburbs, but everybody's continued thoughts and prayers for everything going on here in the US is appreciated.
Thank you very much. Look, we were probably all thinking that. I'm sure there is also someone there from the US, but there is definitely people from everyone. So this is great. Welcome everyone. All right. So this is how it's going to work today. And for many of you who are already familiar with us, you already know how it goes. But Jan is going to present first. Then we're going to have a presentation from Luke, and then we'll take the questions thereafter. However, we have special surprise, and is that Jan is actually going to show us like a modeling type device. I'll let him do the talking, of course. He's the one who understands. But if you have any questions about that, make sure that you put them all in the Q&A and not in the chat, because the chat we use it for other things. In the Q&A, it allows us to actually go through the questions a little bit more organized, in a more organized fashion. So Jan, go ahead. Could you please share your screen? And let's get this done. And if you have any specific questions for Jan, just put them in the Q&A, and then we'll get through to that. And in the meanwhile, just to remind you guys, we are recording the session, and you're going to have access to all the materials and the recordings. Go ahead, Jan. You can start talking.
Yes, thank you.
You can see a Google site.
So I hope you can see my screen.
Yes.
Yes, that's what you should see. Then excellent. So I will just take you to just Google Energy Transition Lab, and this takes you to the Wärtsilä site, wärtsilä.com, and it takes you directly to a tool developed by us. And this is a tool that we started to develop to take a closer look and to understand what is happening to the European electricity market in response to the COVID-19 situation, and what that actually means for the energy systems in Europe. Everything in here is based on free and available data, so there is no proprietary data here. There's a lot of interesting stuff here, a lot of videos, a lot of insights and stuff. And if you scroll down, you actually come to the Transition Lab itself. I will put this into a full screen mode to be easier to show. And what we actually are seeing here, just let me, so this is now data from Europe. What this tool does is that it compares data from 2020 with the same days and same times of 2019. So it's comparing 2019 to 2019, 2020 to 2019, sorry. And it shows how the COVID-19 has impacted on energy consumption, energy generation, how different countries are coping with that situation. We see a lot of stats here on the left. Then we see on the right here, we see the top 10 renewable days, and these are now for the whole of Europe. So May 24th this year, Europe hit 55% renewables penetration. So taken as a whole, we are already above 50%, and the top 10 days this year has been all over 50%, and that's amazing to see. What we also see for Europe as a whole, this is now from beginning of January. So if I drag this slider here to start from let's say February, when the corona virus actually started to hit more and more, we see that the actual load from beginning of February until today is down by 6.6%. While the share of renewables in our power mix is up by 7%. So this is actually showing us now a glimpse of the future. I mean, we are day by day, year by year, we are building more renewables, and we should do so. And this thing, the 7.5% renewable share up is what we would expect to see in 3, 4, 5 years maybe. So this is actually a snapshot on the future that we have the opportunity to take now with this situation. At the same time, we can take a look at Europe here now. Coal generation is down by 30%. Way to go for the renewable targets. This is an amazing achievement. And there's a lot of interesting stuff here. So if you then click on another country, if you hover over a country here, you see a quick stats of Germany, for example. We can then drill through. But if you click on Germany, it highlights Germany, and we see the same stats for Germany, for example. The top 10 days for Germany, all close to 80% even, and I will drill down to April 21st later on and take a closer look on what actually happened on that day. But we also see the same kind of trends in Germany. Load is down, renewable share is up 10%. Coal generation is down almost half. And the very interesting thing actually is that we look on electricity pricing, it's down by almost half. And this is of course putting a big strain on traditional baseload generation, and that is also why we see coal generation go down, because it's not feasible to run baseload coal generation on very low prices. So if we drill down to Germany, for example, here, we go down to Germany, and then we come to another page here. I will click on the overview to start with. So here we see the overview stats, most of the same stats as we had on the first page, but with a little bit more detail. We see here the generation mix on the left, total load, and then we have generation by production type below here. But if we take a look at the total load, I will open this up a little bit more to see more closely what is happening here. So this is now showing. I will click on the blue dotted line. This is the blue dotted line here. That is last year's electricity load. So the load on the German system. And if we then compare that to the total load for this year, we see that the total load has actually dropped quite heavily. And we see it starting here from mid-March something, and that's when the crisis really hit Germany and when the lockdown started to happen. And after that, it has gone down, and we see these are by the way the weeks we see here. So this is the middle of the week, and then the bottoms here, the trues are then weekends. As it usually goes, weekends have lower electricity consumptions as industry is closing down for the weekend, and then it's starting up again on Monday. So you actually see the weeks in the system, and we see here how the COVID situation has impacted on the electricity consumption. So it is visible on countries how this the coronavirus has impacted on the power system. If you take a look at I go to the dispatch system, dispatch page here, and if we take a look at Germany as such, so this is now showing the dispatch of the German system hour by hour, how it really was. You see here now in the bottom we have the nuclear, we have hydro, we have coal, and then on the top here we have light green, we have wind, and then the yellow is solar. And we see in the beginning of the period here, it's still February, so it's the solar is not generating that much due to the winter season, but the further towards the spring and summer we get, the more and more we see of solar generation. And on a high level look, everything looks very fine here. There is no big issues. But if you start to drill down, let's take the one of the top days here. I will move the slider to April 20th and 21st. So take April 19, and then I take the other slider down to April 22nd. Let me take it to 21st then. So 22nd there. So here we have now April 21st, one of the top renewable days in Germany. And we see we have a massive solar peak here in the middle of the day. We have a lot of wind coming in. It was a windy week apparently in Germany, and a good sunshine. And we see here middle of the day in Germany, we see a renewable generation of 84% penetration. We see a total load of 65 gigawatts, and the generation was actually 82 gigawatts, so not really matching there. And the interesting thing what we see here is that we see that the day ahead price in the box there on the middle of the screen, it hits minus 84 euros per megawatt hour, and we see that also down in the graph here on the bottom, the day ahead price throughout the whole solar peak almost, we have hugely negative prices in Germany. And also if we look at the cross-border trading, a lot of export is happening. So in Germany is actually pushing a lot of electricity across borders to their neighbors, and at the same time they have to pay their neighbors to take the electricity of them. This is very much showing on the inflexibility that we see in the bottom of a lot of power systems. That the coal generation that is still online here, the gas generation that is still online, they can't switch off. They need to be running in order to provide electricity during the nighttime hours. So this is one key takeaway that we see, that there is inflexibility in the system. There is also, of course, many of you will argue that inflexibility is not the only reason why these power plants are actually running here, but they are needed for keeping the system stable and keeping the grid running. And Luke will come back to that and have very interesting insights into new technologies for doing that. So if we look here still on this graph here, we see that the load is now 63 gigawatts. And if you look at the solar and wind, it amounts to over 60 gigawatts of generation during the middle of the day here, meaning that Germany actually could have been powered by renewables only during these days. And the same actually goes for a lot of other days during these periods. So it's really interesting to see that even though a country could be powered by renewables only, we are still not there. The systems are not ready to cope with this kind of situation. So we see, if we drill down to the import-export here, in the middle of April 21st, Germany is exporting a lot of power to the neighboring countries. And as I said, as the power price is negative, they also has to pay the other countries to take the electricity away from them. So this is really interesting stats that we can see. If we go back up to the European level, we can take a look on another country here. I will drag the sliders for the days again. So let's take a look at Italy, for example. Italy has now been let's call it the poster child for Corona lockdowns. And if we go to the overview again to see the load curve. So if we look at the Italian load here, same curve again. The dotted blue line is last year. I will highlight that by clicking on it here up. This is the last year data, the last year load. And if we look at the total or the load for this year, we see a tremendous drop here in beginning of March when the lockdown hits in northern Italy, and it's now in the last weeks it's starting to come up towards normal levels again, but it's still impacting on the load. So this is really interesting, and we see the same kind of trends for the dispatch as well in Italy. We see an increasing share of renewables, but we also see that gas. Let me go to this one here and zoom in on Italy, because we have easier to see numbers here. So we see that gas generation, coal generation is all down, and day ahead prices are all down. However, if we look at on a weekly basis, we see that gas generation is actually making up quite a lot of the gaps between renewables and everything else. So even though the gas generation is down, it is taking the intermediate role there in Italy quite a lot. I can still maybe take you to Spain as well, to take another country in Europe. And I do encourage everybody online here to take a closer look. This is open to everybody, as said. So just type in Energy Transition Lab in Google and you will find this page. So if we go to Spain here, again, the same kind of trends. Load is down, renewables are up, coal generation is down, prices are down, all of that. We see the very same kind of things. If we take a closer look at Spain here, so let's start from beginning of February. We see that during the course of time here, nuclear is actually the one that has been taken offline and reducing load, and that is nuclear is then giving space and giving room for more wind and solar generation in the power system. So that is another observation here that again, inflexible baseload generation is giving way for renewable and variable generation. Import export. This is quite interesting if we take a look at the import export here. Spain is both importing and exporting, and we can see during many times and many hours of the day and the weeks, we see that Spain is importing a lot of energy from France and then exporting it directly to Portugal. So actually it is Portugal that is importing the energy from France during a lot of hours. And that is a quite interesting observation we can see here as well. The same kind of thing we see with prices. We don't see heavily negative prices here because the price is not allowed to go negative as far as I know in Spain. And that's why we see that the price is actually, it's hitting a very low of €1, €2 several times during this crisis situation. So by drilling down into this kind of data here, we actually start to see issues, troubles that are coming along with reduced load and with increasing renewables. And this is, as I said, this is what we expect to see in 5 years' time, maybe, when we have built renewables in greater detail and greater amounts into the power system. And I truly believe that this is actually showing us the issues and the challenges that we have today in order to integrate and utilize renewables into a higher degree. And there are very interesting and good technological advancements that are helping us to do this in the future. And I think by this I will leave the word over to Luke, and he can then explain in more detail what are the new and interesting things that we could take forward to make our power systems even greener than this, and actually reach this holy grail of 100% renewable energy power systems.
Thanks, Jan. Don't stop sharing yet. Keep it up for a minute. There's a few questions I wonder if you want to just answer live briefly.
Absolutely, yes.
A couple of them I think are quite simple. One was, what's the color code of each country mean? I don't know if it's just random.
So if we
back on the map,
I believe we are talking about this here. Yeah. So this is the color coding is the amount of renewables and amount of renewable generation in that country. So that is going according to renewable share.
Yeah, great. Another one was related to import-exports, the one in Germany. Which countries in the EU do you think are benefiting most from Germany's negative pricing?
Interesting thing, what we can see if we drill down to that one. Let me just take, I will.
These are questions I have too, so that's why I'm asking.
Yeah, very good. So you let me take the fall here. Excellent. So if we drill down here and take a closer look, so we have Germany is situated right in the middle of the continent, and Germany has a lot of connections everywhere. So Austria, Belgium, Czech Republic, Denmark, France, Netherlands, Poland, Sweden, and Switzerland. And what we can see here is that during, let me see, here is, let me take that specific day again. So 21st of April. So 21st of April, here we see the export in greater detail. So it is actually exporting to all of these countries. It's exporting to all the sides of the country. And interesting thing also is that it's exporting through Denmark, and from Denmark it actually goes all the way up to Norway. So if we click on Norway here and we drill down on Norway, we should actually see that Norway should be importing as well from Denmark to some extent during some hours. So Norway and Denmark are actually benefiting quite a lot. Norway can save on their hydro quite a lot. They don't need to run their hydro, but they can actually save it for a later and dispatch it then to Central Europe at a later time. We also see a lot of power going to Poland, a lot of power going to France. We know, of course, that France has a very big share of nuclear, and it's not always easy for France to regulate downwards and take that on. The same goes for Poland. There's a lot of coal generation in Poland, and it's quite inflexible. What I understood from before as well is that a lot of power actually goes from northern Germany through Poland, through the neighboring countries, and are entering back again in southern Germany. So Germany can also be utilizing the neighboring countries for shifting energy from north to south. And that is then due to internal transmission constraints on the north-south line. So these are the kind of interesting things as well. Excellent question, by the way.
Yeah, I really liked that chart when you had so many countries. So I guess I can take over. There's still lots more questions. More came in as we were talking.
There are
so
a lot more questions.
You can maybe start typing some while I'm talking.
I will start typing, yes.
You can also, what I was telling you before, just have that handy in case you need it later in the explanations. But I think a lot of the questions are repeating themselves. So look, actually, you need to share screen, right?
I think Jan has to stop. There we
All right,
go.
yeah, you can go ahead now.
Okay.
You have 14 open, Jan.
Okay,
Right
then
one.
very good.
Right,
Okay.
look, go ahead. We can see your screen perfectly.
Great. Okay. So thank you, Jan. Thank you, everybody, for the good questions coming in. What I want to focus on a little bit next is some of the projects we've done in terms of supporting higher renewable penetration. So as Jan mentioned when he was looking at Germany, that there was some thermal baseload left running. There's two main reasons that it gets left running, and arguably even a third one. So I'll just mention them briefly. One is that it's needed for the night, and it's too short a time, maybe 4 or 6 hours, that you would need to shut it down, and then it would have to start back up again. Those types of inflexible plants can't do that. The starting and stopping costs are too high, and it makes more economic sense to push through, or it might even be really not technologically feasible with whatever's installed at those older plants. The second one is, as Jan mentioned, stability of the system. So those systems are providing some type of frequency and especially voltage control, that they are forming the grid. You can't even have a grid without that rotational inertia, without those spinning plants. And then third is for security of supply, spinning reserves. So the idea that if some of those renewable plants have some type of issue and trip offline, that you need to have something there that can suddenly increase its output to prevent some type of brownouts or even cascading blackouts across some part of that country or Europe. So those three reasons are really why you see that type of baseload, even when there's so many renewables causing negative prices. All of these services, having technology that can start up and shut down quickly, and having grid stability, ancillary services, frequency and voltage support, and even virtual synchronous generation from batteries that is providing grid forming capability. And the last one of spinning reserves, being able to immediately replace some other asset that trips offline, can all be provided by battery systems and fast ramping engines as we transition to cleaner fuels, especially, that would support higher renewable penetrations. And so I'll talk a little bit through this presentation about one of the software platforms that is a main control center inside of our Wärtsilä product stack. This is just a diagram showing some of the configuration that we have done with our GEMS software power plant controller, where we control multiple power plants simultaneously. Effectively, what our product does in our island projects, which is what I'm going to be talking about in a little bit, is full dispatch and control optimization with an awareness of these costs and requirements, with an awareness of all three of those aspects, whether it's a starting and a stopping timing requirements, that a plant, if it shuts down, has to be down for at least 2 hours or whatever it might be, that there's a battery, or that even the engines are providing primary response, that they're the grid forming entities, that if those assets trip offline, they must be replaced as quickly as possible to maintain the security of supply, and that there's enough spinning reserves, that if any single biggest piece, your biggest coal plant, your biggest thermal plant trips offline and has some issue, that there's enough participating assets, whether it's energy storage or engines or a combination of those, to step in immediately and cover that loss. So there have been a couple of projects which we've tackled, which are small compared to Europe, but the technology has been proven and continues to grow orders of magnitude in terms of the deployments each year, where we are pushing the renewable penetrations further and further with arguably smaller batteries than we did at first. So in the beginning, which I'll talk about on the next slide, there was a battery system on the island that was more than enough to even cover the whole load. And that's not realistic for Europe. For Europe, battery technologies are being installed more and more, but they're not going to be at a level where the whole grid can be carried by batteries. And so this project here in the Caribbean is really relevant because it's a small battery. It's a 6 megawatt battery on an 18 megawatt grid. And so here the battery is big enough to cover a loss of half the wind farm at any time, as well as a loss of each of the large engines at any time. So it's sized for that spinning reserve application, and it's a grid forming battery. So it can start up like a UPS. It can bring up the whole grid all by itself. And then once that grid is up, then you can synchronize other assets to it. So it's the same as like any type of thermal spinning plant. It's providing virtual synchronous generation. So it's forming that grid. It's running in parallel with the engines. And it responds very fast, sub-second, sub-cycle. So within a few kilohertz, it's already going to be dynamically adapting and starting to output power when the frequency starts to dip. What we see in Europe is that thermal plants get left on to create this voltage, to create the potential difference so that the grid can even exist. And if more and more batteries can be brought onto the grid, then the grid can be formed by those batteries and the renewables can flow freely. And so our project that was completed last year in the Azores, right off the coast of Portugal there as part of Portugal, is 100% renewable capable, that we can switch off the thermal generation completely and form the grid with the batteries in virtual synchronous generation mode, so that those engines can come and go from the grid as they please, that there's always a voltage and a frequency to synchronize to. And this is a really important piece of that puzzle, is having that type of technology. So just diving in real quick to a little bit of technical detail. This may be too technical for some of you, but I hope that I am able to explain it in a way that helps demystify some of the electrical engineering complexities that are going on under the hood. So effectively, there's two main dimensions. There's real power, which is shown here on this x-axis, and there's reactive power, which is shown here on the y-axis. Every grid has two things, voltage and frequency. Frequency is effectively the pulse of the grid, and voltage is effectively the blood pressure. You can think of all the transmission lines as pipes, the energy's flowing through them. And you need both of these. Without the potential difference, without the blood pressure, the blood won't flow from one point to another. Without that pulse, the frequency, you don't have that inertia, that ability for the system to actually maintain and remain electrified. And so historically, we would have been in this number one area, which is shown by two different dots. The orange ones represent, sorry for the little bit of confusion here maybe. The legend just shows that this left half of the circle is consumption. So the negative loads are consumption, and the green side is generation. And so this is the, this depicts the operating region of everything. So generation is always going to be on the right here. And so historically, when there were not very many renewables, there was a lot of thermal generation. So this orange one right here shows that there was Most of the real power would have been produced by the thermal plants, 90% or so. And all of the reactive power requirements would have come from those thermal plants. Early renewable plants didn't produce much reactive power, if any. And so existing thermal plants would have had a reduction in power factor quality, and they would have had to produce some of that reactive power. But over time, renewable plants began to be specified in a way where they had to at least provide unity power factor. And so as time went on, we see these thermal plants, oops, sorry, I didn't mean to go forward, continue to produce less real power. So it shifts from 1 to 2 here. Meanwhile, the renewables are producing more power. They're producing a little bit more reactive power. So 2 is a little bit lower than 1, but they're not often producing a lot of reactive power to actually support the grid in any way. And then 3 would be where things are moving to, where more and more renewable plants and battery systems are being specified to actually produce reactive power proportional to their real power generation. So in line with the power factor. And so that really helps, because now these renewable plants that are generating have to produce a whole bunch of reactive power as well. And today that's what's happening a lot across Europe, is that those renewable plants are producing a lot of reactive power as well to serve the reactive load needs. Reactive loads are like spinning motors, compressors, air conditioners, things like that. And where we really need to get to with Europe is this number 4, where we've gotten to on some of our projects, and where we have technology in terms of battery inverters that are forming the grid. You're not necessarily getting the reactive power from those batteries, but they're the thing that's actually producing the grid and is able to output P and Q, real and reactive power. And that's what enables you, is when you have renewables plus battery in green at this 4, that renewables plus battery are producing all the P and all the Q that you need together. That's when that enables you to actually shut the engines off at number 4. Otherwise, your thermal plants, turbines and engines, remain trapped up here at this 3, because they can't go below their minimum loading. They have some minimum loading, call it 30%, and they can't push lower than that. And so you have to keep them running just to provide the reactive power support. And the grid is hovering, somewhere between this 2 and this 3, based on the minimum loading on the real power dimension here. So hope that wasn't too technical, and I hope that helped a little bit, but it's effectively the fact that those thermal plants can't go to 0 when a battery can. And then even when the battery is at 0 loading, it can still produce reactive power to keep the grid up as it needs to. And so here I just share an example from our Azores project where, again, loads are very low compared to mainland Europe, but the reality of having volatile renewables and a battery that is dynamically stepping in to fill the gap. The battery is in green, wind is blue, yellow is solar. And this is just a 1-hour view. Brown is a thermal plant, an engine that gets turned on once the renewable forecast has come down and that battery has been used for that loss of wind scenario. And this whole time, this exact same hour, the grid frequency is very stable and flat. And the voltage is very stable and flat, because that battery is providing all 3 of those services that we talked about in the beginning, that it's stepping in to fill the gap whenever it needs to and balancing the grid so that we can have those engines completely off. Just as a brief ending note before we go to all the Q&A, this is just a few minutes snapshot when the batteries, during one of the maintenance periods when we had them disconnected from the grid and then reconnected them to the grid. You can see a difference in the frequency quality. The batteries in grid forming mode, virtual synchronous generation, add a lot of stiffness to the grid. And so you can see that while the engines are oscillating around, once those batteries join, they're very fast and lightweight and responsive. They don't have the actual inertia of an engine, but they create synthetic inertia that's actually cleaner and smoother than a thermal spinning plant can provide. And you can see that evidenced here in the data by itself. So I think with that, we can go to Q&A.
Can you stop sharing, or let me do that for you?
I can, no problem.
Oh, perfect. Yeah, and I'm gonna open your microphone. No, can't. You're gonna have to open it yourself again.
Oh, yes.
So you've been busy, but still, you know, you're just managing to keep up with demand.
I can't answer all the questions. There are coming a lot of questions, a lot of excellent questions as well. So keep them coming.
Is there anything that you need to show again, or is there any question that you'd like to show the graphs for, or can we do without the graphs again?
I think we can do it without the graphs.
Okay. Would you like to start with any specifically you were looking at? Otherwise, I'll just read a few from that.
I had a question answer box open here, so I can take one here. What happens to the system when no country can import? And I think Luke, you can also give an answer to that as well. That is an excellent question, and I think that is a thing that we most likely will see more and more of in the future. I mean, if you look at a lot of country plans and national energy and climate plans, countries are talking about that we have the interconnectors to neighboring countries to export and to give some flexibility to our power systems. However, when we go forward into the future and we have a lot of renewables and we have a renewable baseload, we will for certain run into the situation that we have a lot of wind, we have a lot of solar, and we have more energy than we need. And also, if we have that, our neighbors most likely have the exact same situation. If it's sunny here, it's most likely sunny on the other side of the border as well, and they have the same kind of issues. So nobody can really import. And this is a situation that either you start to curtail, so you reduce the generation from wind and solar, and that we, of course, we don't want to do that. So one thing is what we've been talking about, energy storage. Of course, we can store it for later use, but I would also say that we need to start to look into other technologies, other ways of utilizing this energy, free energy, by the way, and that should be sector coupling. Turn it into charging our electrical vehicles, turn it into synthetic fuels, turn it into heat if you are living in a northern country where you need heating, or turn it into air conditioning and cooling your houses if you are living in a hotter country. These are the kind of things that we need to start to look into more and more. Luke, do you want to add on that?
No, I think that's fine. Yeah.
There was another one. In the case of Germany, why the renewables are not switched off to avoid negative export?
That is of course due to the fact that renewables actually have grid priority. So renewables have access to the grid automatically. So they don't need to modify their generation. They just generate and they export everything to the grid. While then the transmission system operators need to make sure that the grid is stable, that you have the balance in the system, and that actually leads to the negative pricing. So the renewables have grid priority actually, and that is the reason why. And I still believe it based on the answer that for the previous question, I think renewables should have grid priority.
I think the EU has announced that they're going to take that away. The ability to give any grid priority.
That is probably being discussed. Yes, I still hope that it will be kept in this very way. Anyhow, of course, during emergency situations, if you would have a very unstable system, if you would not curtail, then of course yes, you need to curtail in that instance for sure.
My understanding is that it was a more political matter, so they took away the ability to prioritize any specific sources. But because I don't know enough about it, then I better not add anything here. But I'm sure someone in the audience knows, and if you do know the story, feel free to send it through the chat.
Yeah, I think the reason that it's hard is because someone has a PPA and they've agreed to some price and offtake, and you can't. It's a contractual agreement. So curtailment is one of those things where it has to be in the PPA. You have to reserve the right to curtail somebody ahead of time. and
It
have
was more that
something
some of the
like
red countries, they were prioritizing coal. So the only
Sure.
way to stop that was to take away the ability to prioritize any source of energy specifically.
Sure.
I think it was something along the lines. But anyway, as
So-
I don't know the topic in detail.
Yeah. So there's a question from Ignacio.
Go for
Why
it.
scenario thermal one real power is not 100%? It was a long time ago, but I didn't want to put it all the way there because for a long time we've had a few percent renewables, which are growing rapidly. So I put it less than 100%, but it could be. It was, you know, even I would say maybe it never was. There's always been hydro, geothermal, other things like that. So it depends what you put in that bucket.
Just a
There's
question.
another. Oh,
sorry, that was repeated several times, Jan. But about doesn't reflect the changes between Spain and Morocco.
I was actually typing an answer to that, so excellent that you brought that up. Yes, the Spain-Morocco interconnector, that is a vital one, and I know that there's a lot of energy exchange going from Spain to Morocco. The reason why this is not reflected yet is that this information is not directly available from the NSOE link. So we need to look into how to import that in a good way in there. And of course, we need to draw a line somewhere where we just cut it. Otherwise, we will have the whole globe in there.
So far you have just this European countries.
For the moment, we have only Europe, and that is of course due to the reason that we are getting this data, free data, free for everybody. So we are just this is not our data. We are getting this data, and we are just putting it into a visual format that you can actually scroll it, look at it in an easy
and
way.
analyze it easily.
Yeah.
Sorry, I interrupted you, Luke. I also wanted to give you some time to take a look at.
Oh, no, it's
the other
fine.
questions.
It's fine. I think I want to answer this question briefly from Julian. Let's see here, answer live. Can you explain which steps Wärtsilä GEMS works in a typical project of renewable energy, mainly solar and wind? Yeah, so we can work as a company, Wärtsilä, we can work with you to find solar and wind vendors that you can partner with. At the same time, you can go shop for those technologies yourself. Since we don't sell wind and solar for the most part. There are projects where we have wrapped the solar component. So if you want a fully integrated system with battery and solar from one provider, we can subcontract that solar part out underneath of us as needed. But most of our projects, our customers have procured or are in the process of procuring those renewables completely separately. And there's simply a control scope within our contract to control those renewables. And so we have a requirements document to provide to that vendor in terms of what types of interface and set points we'll need to be able to set. And that's all, worked through during that contracting period. I think that answers that question.
Just keep going if you like with the other
questions
ones.
standing out to you guys?
There is a lot of other new questions that are coming in as it happens. It says, for example, how do you expect to solve the legal constraints, TSO, DSO, that can own storage assets? This is a problem in Spain, actually. There isn't such a thing as a storer. So how are you going to work around this?
Yeah, we've seen it in a few places globally. In Texas, here in the US, there was a ruling recently where energy storage was deemed, I actually forget which side it fell on. I think it was deemed not a generation asset. So it was deemed a transmission and distribution asset. So it had to fall that side. And that was frustrating for some people because then you couldn't participate doing energy arbitrage and things with the battery and the generation side. So we've seen other examples though of it done right. So if you look at California and you look at Australia, all of the market rules are such that any asset can, if they qualify for what's actually required in terms of producing electricity. So you can register as a generation asset, and you actually in Australia register as a separate load asset. And so your one battery has to register as two different market facing entities that get bid together.
One question, if I may interrupt you, sorry.
Yeah.
Should, throwing out a question here, basically to you as well, should we actually introduce a third alternative in the grid code: generation, consumer, and storage?
Yeah, so I don't know that it should be a third one. We see it, so in the difference between Australia and California, which is interesting, I think as a global, as the world continues to evolve here, we all need to look at what different parts of the world are doing globally and see what's working right and what's not working. But so in Australia, where you have to be a load or a generation asset, or there's a third one there that's like an intermittent renewable asset where you have a forecast, but you don't have to follow your dispatch so closely. You can just generate as you need to. And California is similar, but California is working on some new classifications, which are available this year. There's a few plants going in this year that are hybrid, where there's an energy storage and a renewable at one point of interconnection that is getting bid as one asset. So it can charge, it can discharge, and it can do renewable activity. But in Australia, that plant would have to be 3 different interconnections, but in California, it's allowed to be 1 power plant. So there's different ways of tackling it, and it really comes down to the system operator in terms of what technologies they have and what technical debt they have in their way of working. If they have challenges in terms of how they dispatch and clear bids and get plants to operate that can't be overcome unless they do it a very certain way, then it comes down to investing and upgrading what's happening inside of that dispatch and bid optimization software at the TSO level.
Yeah. No, I think I actually wanted to ask that question to you before, so now I got the opportunity to do that.
In a public setting, it's good.
Yes.
And you're sharing knowledge, which is awesome. There is a question here about, is it reasonable to harmonize the grid codes in the EU? I think there is a harmonization effort.
That is ongoing.
UE 2006/631. There is a law, and there is like 3 years to finish, to finalize it. So I think we're going in that direction. Am I correct?
Yeah. We are going in that direction. I'm not familiar with all the directives and paragraphs, so I can't answer on that. But I know that there is a lot of initiatives going on, and I know that the transmission system operators and ENTSO-E, the umbrella organization for that in Europe, they do have a lot of work groups working on that, and we see more and more of for example, reserve transmission system or power system reserve sharing, so cooperation on that and grid cooperation stuff coming up. So a lot of countries are starting to share reserves with each other and these kind of things. So yes, we are going more and more towards an integrated grid.
And I think from last year, actually, as it happens, we have a webinar in a couple of days, but it's about Spain, about how the grid code in Spain is adapting to the one directive from the EU. So I know there's certainly something going on, but I don't know the details all that well. So again, you know,
I have a good one.
Yeah, sorry. Go on, Luke.
Milenko asked, second from the end of the questions, should battery be used 3 times a day for morning, afternoon, for demand management, shaving peaks? Currently, my understanding is batteries are discharging only once a day. There are batteries today that do 3 to 5 cycles per day. Most of the ones that are doing that type of energy throughput are doing ancillary services, frequency response, where they are just very dynamically little bursts of microcycles, always switching, charging, discharging all day long. They're not really doing anything that's intentionally doing a discharge here and a charge there. Most systems that are set up for some type of arbitrage are set up at the highest price time of day and the lowest price time of day. And so those ones would only do 1 battery cycle per day. So I don't have a straight answer. It's not that a battery should do one or the other. The business case for each battery is dependent on the context, what markets are available, what your tariff looks like, all that kind of stuff. And you need to figure out that side of the equation first, because if you're planning to buy a battery that's only going to do 1 cycle per day, that battery is cheaper than a battery that does 3 to 5 cycles per day. It'll also last longer. And so it's all baked into how you approach the business case, and what type of battery technology and sizing you do ahead of time. Because if you're going to drive the battery a lot harder through its lifetime, 3 to 5 cycles per day, you need to buy a system that's capable of doing that. They're not all equal. And if you buy a battery for 1 cycle a day and then start driving it 2 and 3 cycles per day, you will kill the battery sooner. And maybe that's okay. If you suddenly have access to a new market that actually pays for you to do that, that's fine. But you have to have the right warranty terms in place, the right performance guarantees, and the ability to have that type of flexibility with your asset in the long run.
So you need to plan a lot and optimize. Go, Jan,
maybe I can add on a couple of sentences. That is quite an interesting thing. I agree completely what you said, Luke. What we see in Europe is that more and more projects and investors and developers are looking more and more into this, let's call it merchant projects, where you are not really doing ancillary services, but you would be doing arbitrage on day ahead, intraday balancing markets and all of that. And this, of course, opens up for a really, really interesting optimization challenge. How do you optimize a battery on something that you have no clue about how it will look like tomorrow? You don't know what the market will be tomorrow. Will it be good prices, bad prices? You have an idea, but you don't really know. So it's a really interesting challenge to make a business case out of that. But the world is moving towards that direction, and we are on that track as well.
Yeah, so I want to add one more sentence to what Jan said, which is that he's exactly right. It's like any business. If you have to have a little bit of risk appetite, you're not going to have a business case for a battery that's so rock solid it's guaranteed to make you piles of money. You know what I mean? That's just not how it works. You take some risk, you plan very carefully, and the key piece to make sure that you're not overly exposed is having a performance guarantee. So you base your business case on some type of conservative approach. You say, okay, if I do arbitrage every day, and if I have some conservative view on the price delta, I can make the business case for this battery, but I'm not really making money. I'm scraping by. But there's probably going to be more volatility. There's going to be new ancillary service markets. There's going to be growing renewables. And in that context, I'm probably going to make more money than that, but nobody has a crystal ball. So you have to have you have to then go source and procure a battery that has the right type of warranty and life cycle guarantee that if you do 1 cycle per day, it will last 10, 15 years. If you do 2, 3 cycles a day, you still have some benchmark. It will last maybe 7 years, and that you have a framework where you know that if you do certain things, what those implications are, so that through the life of your asset, you're able to dynamically adapt to those changing market conditions.
Okay, we're coming to the end of the time. So is there any burning questions that you guys want to answer there at the back of this? Just a final one or anything? There was one here that was very interesting, but I'd rather you pick ones that you might want to answer more. We have a few coming in now.
Yeah.
The one that I had is like, seriously, literally, we had 30 gigas coming in Spain in the next 10 years of PV and another 10 of wind. Italy, something similar. I mean, is this even doable? Like you're going to end up with such peak loads that you can't even consume at those times. So unless you're doing a really good job with optimizing, this energy, how do you manage that? Yeah, go for it.
I think this goes back to the answer that I gave to another question before. I mean, we need to start to optimize everything together. We can't continue to sub-optimize the electrical system, and then we sub-optimize the transportation, and then we sub-optimize the heating, cooling. We need to optimize everything. And I'm talking about, of course, of sector coupling here. That is the way we need to go. And when we have a huge amount of excess capacity, we need to turn it into synthetic fuels that can be used. For example, hydrogen that can be used directly at industries, and then other types of synthetic fuels, maybe for transportation, maybe for power generation, for other sectors. I mean, we need to take to start to optimize everything. If we look at Europe today, I mean, the electricity, the energy that goes to electricity or is consumed as electricity is only 1/4 of the energy consumption in Europe. Half of it goes to heating and cooling, and the last 25% is for transportation, roughly speaking. So we need to do a more sector coupling and more complete optimization of the system. That is my belief, and then for sure we will be able to take care of these 30-20 gigawatts of additional solar that are planned.
Cool. Okay, some last words from you, Luke, and we have someone that's actually joined from Los Angeles. It must be quite early there.
Yeah, I want to answer one of the last questions. It asks about regarding battery lifetime, how will batteries be disposed of without violating environmental regulations? So just briefly, what's inside the batteries is basically metal. It's different types of metal layered and stacked in there. There's the electrolyte, but again, it's highly recyclable. Honestly, the reason we don't see massive battery recycling yet is because of economies of scale. We're seeing this more and more with PV, that it's gotten to a point where there's enough silicon panels that are reaching end of life, that there's piles of panels sitting around. People who are entrepreneurial are collecting those, and they're highly recyclable. You can melt them down and re-extract the same elements out of them, and you don't have to mine for them. You just melt them, separate them, use them again. The same thing goes for lithium-ion batteries. As we get more of them, the recycling opportunity, as mining continues to be a challenge and limited resources, once we have all these already separated, it's arguably easier to separate out from a battery than it is from the raw minerals from the rocks. So I think there's a lot of potential opportunity for business there, and it's just a matter of time before there's enough to have economies of scale, enough momentum to make sense to invest in building those types of infrastructures. And we already see it at with various battery vendors globally, that they have they're very willing to include end of life in the contract from the beginning. We see it often in different RFPs and proposals where it's actually required that we bid and include a price for when it gets end of life, that we come take it away, and we partner with the different battery vendors to do that.
Well, thank you very much, Jan. Thank you very much, Luke. You guys have any further questions? You guys are available. They can reach out to you, correct?
Absolutely.
Your emails are in the presentation, if I'm not wrong. So, or get in touch with us. We'll put you in touch. And thank you very much for being here today. I don't know if this is of interest, but in the topic of recycling, I know the World Bank Energy Storage Partnership is bringing out some actual reports on what can be done in terms of recycling and reusing. So I would recommend those because they're really like full reports, and they're available for everyone. And as I said, get in touch with Luke, get in touch with Jan. They'll be delighted to hear from you. And I'll see you in the next time. Thank you very much.
Thank you.
Thank you,
Bye-bye.
guys. Thank you. Bye.